In this video, we discuss the concept of the basis of a vector space and the dimension of a vector space. The idea behind determining if a set S spans a vector space V is to see if it contains enough vectors to describe all the vectors in V. And the idea behind determining if it's linearly independent or dependent is to see if the set contains any redundant vectors or not. So basically, if you combine these two concepts together, that would mean that this set S has exactly the right amount of vectors to describe all of the vectors in the vector space. And this brings us to our definition of a basis. So basically, a set S is a basis for a vector space if it satisfies the two properties where the set spans the vector space and the set S is also linearly independent. Okay, so the main focus of this section is going to be to determine when a given set forms a basis for a vector space. And so we basically combine the two concepts from the previous section, right? So if you remember, the way we try to analyze these sets of vectors is to form a matrix where the columns of the matrix are the individual vectors in the set, right? So V1 is written as a column vector in the first column, V2 is written as a column vector in the second column, and so on. So in the case of the standard finite dimensional vector spaces, these two conditions on spanning and linear independence will be satisfied exactly when this matrix A is a square matrix and is invertible. And so from what we learned from determinants, we can check invertibility if the determinant of the matrix is not equal to 0. However, for subspaces within the standard vector spaces, typically A will be a rectangular matrix with more rows than columns, and in that case you need to look at the row reduced echelon form to determine whether it's a basis or not. So the fact that a basis satisfies the two conditions for spanning and linear independence gives us this property here where once you have a basis, every vector in the vector space can be written in a unique way as a linear combination of the basis vectors. So we don't use this concept so much in this particular section, but it will be the focus on section 4.7 where we discuss coordinate vectors and how to represent vectors in different bases. On this page, we look at the standard basis for some of the standard finite dimensional vector spaces that we use throughout throughout these chapters. So the first vector for space we look at is R3, and here our basis has three vectors. Right, so the first basis vector is 1, 0, 0. The second basis vector is 0, 1, 0, and the third basis vector is 0, 0, 1. Okay, so from what we said previously, right? So to verify this is a basis, you take each basis vector and write them as column vectors, as I did here. And you can see that this matrix here is clearly invertible, right? Because it's just the identity matrix and the determinant is 1. So our set S is a basis for R3. And furthermore, this is called the standard basis for R3. Basically because if you take an arbitrary vector in 3-dimensional space, right? So say vector x has components x1, x2, and x3, and we can write our arbitrary vector in terms of the basis vectors in exactly this way, where the 3 components of our vector form the coefficients for the basis vectors, right? Because if I take x1 times e1, that gives me the x1 in the first coordinate. Then x2 times e2 gives me the x2 in the second coordinate. And x3 times e3 gives me the x3 in the third coordinate. And so the representation of our vector x in terms of the basis vector is exactly the same as the typical coordinate representation that we have for 3-dimensional vectors. And so this is why this is called the standard basis. And so basically the individual basis vector just separates the coordinates of the vectors in R3. Okay, so if we look at Rn in general, we can construct the standard basis in exactly the same way, right? So for Rn, we have n basis vectors, which we'll call e1, e2 up to en, and each basis vector ei is set up so that it has a 1 in the ith coordinate and zeros in all the other coordinates, right? So for example, in R5, if I take e4, it'll have a 1 in the 4th coordinate and a 0 in the other 4 coordinates. And so if we do the same thing as we did in R3 and set up the matrix with the basis vectors as column vectors, again you get the identity matrix, which is again still invertible. So this shows that S is a basis. And again, if you take an arbitrary vector in Rn and write out the representation with the basis vectors, then the coordinates of the vector x are just the coefficients for the basis vectors as linear combinations. Okay, so so continuing on here, now we look at the vector space of 2x2 matrices. So this vector space has 4 basis vectors, and so now the basis vectors are 2x2 matrices, but essentially they're set up in the same way, right? So you notice how in each basis vector I have a 1 in one of the coordinates and 0 in all the other coordinates. So this has a 1 in the top left coordinate, this has a 1 in the top right coordinate, this has a 1 in the bottom left coordinate, and this has a 1 in the bottom right coordinate. And and again, to verify this is a basis, I write them as column vectors, right? So each basis vector has 4 coordinates. So as a column vector, this would look like 1, 0, 0, 0. This is 0, 1, 0, 0. This is 0, 0, 1, 0. And this is 0, 0, 0, 1. And again, it forms the identity matrix. And so you will see that in all of these standard vector spaces, the standard basis follows this general form where the basis vectors look like this, and when you set it up in as a column vector, it looks exactly like the identity matrix. And the reason, again, that we set up the standard basis in this way is if you take an arbitrary vector in the vector space, what the basis vectors do is to separate the individual coordinates of the vector, right? So the first basis vector separates out the first coordinate, the second basis vector picks out the second coordinate, and so on. Here we look at the vector space of polynomials of degree less than or equal to 3. So in this vector space, we take as the basis vectors these particular polynomials, so which are just the powers of x, right? So this is x to the 0 power, which is just 1. This is x to the first power. This is x to the second power. And this is x to the third power. Okay, so here we can look at the basis vectors v1 through v4 in the following way, right? So really the vectors here go up to degree 3, right? So the polynomial 1 really should be thought of as 1 plus 0x plus 0x squared plus 0x cubed. And the polynomial x is actually thought of as 0 plus 1 times x plus 0x squared plus 0x cubed, and so on. Right, so each of these are thought of as third degree polynomials, where the coefficients are 0 if it's missing a particular term. And so if we think about the vectors in this way, then we can represent them as column vectors in exactly this way until we again form the identity matrix, which is invertible. And so we see again an arbitrary polynomial in this vector space can be represented in terms of the basis vectors, where the coefficients of the basis vectors are again precisely what we think of as the coordinates for the vectors. Okay, so now that we've discussed some of the standard bases for vector spaces, let's look at non-standard bases. Right, so a typical basis doesn't have to look like this. So in this first example here, I have 3 vectors, and we want to see that this set of 3 vectors is a basis for R3. So we set up these vectors. So this is my v1, v2, and v3. Right, so I set them up as column vectors: 1, 5, 3, 0, 1, 2, 0, 0, 6. Right, so this is v1, this is v2, and this is v3. And so I have a square matrix, and so now I have to tell whether this is invertible or not, and I can do that by calculating the determinant. Right, so, and this is lower triangular, so the determinant is just the product of the diagonal entries. the determinant of A is just 1 times 1 times 6, which is equal to 6, which is not 0. Right, so that means that A is invertible, and so S is a basis for R3. Okay, so let's continue on to example 2. So here we have the vector space of 2 by 2 matrices. Right, so my set S has 4 vectors in this case. So again, to verify whether this is a basis or not, I set up the matrix with as column vectors. So this one will be 1, 2, negative 5, 4. 2, negative 7, 6, 2. 4, negative 9, 11, 12. And then 1, 1, 1, 1. Okay, so now we can determine whether this is invertible or not by calculating the determinant. And I've already previously calculated the determinant. And so we see this is our matrix here, and then I've calculated the determinant as 433, which is not equal to 0. So that means that S is a basis for the space of 2 by 2 matrices. Okay, so basically, for if you have non-standard basis, we can just set up this matrix here and calculate the determinant to verify whether it's a basis or not. Okay, so here the property in this theorem states that for a finite dimensional vector space, all bases for the same vector space should always have the same number of vectors. And so this gives us the concept of the dimension of a vector space, which is defined as just how many vectors are in any basis for that vector space. Right, so for our standard spaces, right, so Rn has the basis vectors e1 through an, right, so that means that the dimension of Rn is just n, and the dimension of the space of polynomials up to degree n, so this basis has n plus 1 vectors, right, because you have all the powers of x up to n, and also the constant polynomial 1, right, which is just x to the 0 power. So the dimension of this space is n plus 1, right? So we saw that P3 has 4 basis vectors, so that had dimension 4. And then the dimension of the space of m by n matrices, right? So there's m times n different coordinates, so the dimension is m times n. Okay, so what that means is that once you know what the dimension of a particular vector space is, if your given set does not have the correct number of vectors, then it can't possibly be a basis, right? So in these two examples here from the previous page, if this set S did not have three vectors, then it can't possibly be a vector space. But because S does have three vectors in R3, it may or may not be a vector space, and so we can verify it using the determinant. Okay, so in the next couple of examples, we'll look at subspaces in these standard vector spaces and see how to extract a basis for the subspace. Right, so here we're given the subspace W in R3, where the Y component is arbitrary, the Z component is arbitrary, and the X component depends on Y and Z. Right, so thinking geometrically, we'll see that W is the plane in R3 given by X equals 2Y minus Z. Okay, so we want to find a basis for this vector space, right? So what we can do is we can take an arbitrary vector, right? So this is what an arbitrary vector looks like. And what we're going to do is we're going to separate the free variables. Right, so what do I mean by this? Right, so take W, so just this vector here, right? So 2s minus t, comma s, comma t. Right, so I want to separate the s and t. So I can write out the three components in this way, right? So the first component already has both s and t. The second component only has s, right? So I can just think of it as s plus 0t. And then the third component doesn't contain s, so I can think of it as 0s plus t. Okay, so now I separate the s and the t, right? So the first component is, so I separate it using vector separating as two separate vectors, right? So the s, first component has 2s, the second component has s, and the third component has 0s. And then writing it with the t's, right? So minus t in the first component, 0t in the second component, and then t in the third component. Right, so if you recombine these two vectors using vector addition, you see you get exactly this, right? So really I'm just separating this vector into two separate vectors. Okay, so now I can factor using scalar multiplication, right? So each component contains s here, so I can factor out the s. So then what's left over is 2, 1, 0. And then from this vector I can factor out the t. What's left over is minus 1, 0, 1. And so what this says is that any vector w in W is a linear combination of these two vectors here. right? So that means that these two vectors span W. So our two vectors 2, 1, 0 and minus 1, 0, 1 spans W, right? Because again, W is arbitrary, right? So that means that any vector in W is now written as a linear combination of these two vectors. Okay, so this set spans W. So now to show that this set is a basis, I need to show linear independence. And so what does it mean for linear independence, right? So this means that so if this is V1, this is V2, so C1 V1 plus C2 V2 is equal to 0 has only the trivial solution. Okay, so we can check this by just setting up the system of equations with these as column vectors, right? So 2, 1, 0 minus 1, 0, 1 is equal to the 0 vector. This was V1, this was V2. Okay, so I calculated this previously, right? So this is our augmented matrix. And so we take the row reduced echelon form. And we see that so this first column is for C1, this column is for C2, and so reading off row 1 and row 2, we see that C1 equals 0 and then C2 equals 0. And the third row is 0 equals 0, which doesn't do anything. And so this is the trivial solution. And so this shows that S is a basis. Okay. So we have a basis for W. And what is the dimension? Well, S has two vectors, so the dimension of W has to be 2. And so that corresponds to what we have geometrically, where W is a plane, which is two-dimensional. Okay, so this next example here is similar to the previous example. So we have this subspace W defined in this way, and we need to find a basis and determine the dimension, right? So our arbitrary vector W has one free variable, T, So it's a simple matter of separating it, right? So I can just factor it right out. Right, so this is going to be my basis vector. And this equation here just shows that it spans W. And it's also clearly linearly independent, right? Because a single non-zero vector by itself is always linearly independent. So S is a basis. And has one vector, so dimension of W is 1.